hurried or something, just take a break, go back, do the dots, color them in while you think. Don't be in such a hurry like I was. See, I forgot. I even started coloring it before we did all the bonds. But this is a neat amino acid because there's 2 nitrogens in it. And see, I got to get in the habit of drawing these triangles bigger, okay? Later, when you're good at this, you'll be drawing it in ink. You never use pencil, ever. You can color in with it, but your notes, always in ink. So as we do the ring here, it's the number of bonds is what we need to focus on. Let's try and straighten this up a little. We're counting bonds. I see 3 on this nitrogen. Color it in. There's, let's see, the double bond is to the carbon. Boy, I really messed this. No, I didn't. Okay, so there to there to there. So that's got its 3 bonds. You color it in now. I see I colored that nitrogen in when I should have put the hydrogen dot on. Now, the diamonds. The structures won't draw the hydrogens, so you got to know your double bond, single, there's 4 for that. So take your time. I'm trying to rush it here. Remember that carbon there? See, it's all its bonds are to carbons. That's called the sp orbital. There's sp2. And there's a methyl that's called the sp3. No sp3s in this for the professors that would be testing you on this stuff. So it's easy to look now because a lot of people like to just count the hydrogens and see what the structure is. But this, just look, because nitrogen's the equivalent of a carbon because of the electronegativity. So it's sp with a, let's put an N up there. So the strength of all those bonds can be determined from what you call the molecular orbital theory. This pi bond has a certain energy, these bonds. So to break this up or make it, you can figure what the free energy is. That's what they like to do. So I see a carbon here. It's got 1, 2, 3 bonds, right? Put that dot. There's the hydrogen, the 4th. Color it in. So now we're done with it. What's this carbon? 1, 2, 3. It's got a double bond, so you got to figure it ain't going to have no more. It gets a hydrogen. So once you get the hang of this, it's pretty consistent, especially carbon. That's what's so beautiful about the element, being right in the middle of the table. 4, tetrahedral. The spatial dimensions of carbon make it unique. The bond energies between carbon and carbon itself, and the fact that it can do a double and triple bond. I mean, God couldn't be more brilliant when he came to this because he made it so simple. Okay, so this is the side chain, and we're going to clean this up considerably here. See, we're using all recycled material here too, kids. That's why some of this gets a little dirty and messy. But look at this. I find brand new purple thick Sharpies. See that thing? Look at the point on that baby. Okay, so that's cleaned up a little. This was our warm-up. Now we're going to focus on histamine. Boy, what a cool technique was that. Take 3 pencils and just kind of do a squiggly line on it. It's like triple DNA. They actually do that. They'll have a strand of DNA and bring a single one, a double strand, and then bring a single in, and the third will kind of wrap around like that. Okay, so we're back to histamine. From this here, we learned our mistakes. We're going to leave more room at the bottom. And see, I'm trying to think of you guys not knowing this stuff. Since I know the backbone, this is what I usually don't even focus on. I would just draw like a straight line across there. But for you guys, we're going to keep it in mind. Because look, it'll show. This would be what a histidine... Let's see. We need to focus on this part, though. That's why I was doing it good. Because all that's going to happen is It's going to be in the middle of a chain to the point where there's one carbon, the side chain. And the nitrogen has to be to a side carbon out there. So the O with the double bond here, this is what's so important on this. If this is on the end, it's a carboxylic acid, right? So what it gets is the O with the dot. Remember the red dot? Well, do you know what that is so close to already being? It's almost already carbon dioxide, right? So you'll amaze your friends when you know the difference from the amino acid histidine. You get that when you're eating, the food you eat, the proteins go on. You can make histidine do other things, because histidine, I believe, is an essential amino acid. So it's going to come into your body in the form it already is and have function. I mean, it's going to work the way it is. So there's going to be one enzyme, I won't name it here to confuse you, that's going to cleave the CO2. Now what you focus on is the OH up there, because what do you need to do? Take the proton away and get a double bond in there. Take away the proton, the electron pair stays. So then all of a sudden it's able to do the bond, but you got to break a carbon-to-carbon bond. But you're going to find from electronegativity, that's why it's exactly like magnets, kids. I can't tell you. This CO2 is hanging on the end. When you get that proton off and strain this bond in here, it's exactly like having, say, 3 magnets hanging. The 2 are going to drop off because the mass overall, say you're swinging it even, because these things are in motion, right? The enzymes are so beautiful that they're able to fit the rest of the molecule in a certain way to apply pressure and then have something up here that's going to want to take away the proton and let that form a double bond and go off as CO2 gas. And CO2, see, we're starting to see these molecules play many different roles over and over, and the more you become familiar with them, I'm already thinking of the way CO2 looks, because the way we drew at that time, it gives it that 3-dimensional thing, right? So the enzyme, we're just going to break it off here, takes CO2, we're going to draw right here, how about that? Diamond, double bonded O's, right? Let's see, let's do it, it's got to be this way, I guess. There's an O, dimensionally. It's not going to be 2 O's down here. They're going to be farthest apart, because like magnets, you know, we got to draw those aliens in. I was trying not to confuse you all with electrons and stuff, but you have these lone pairs of electrons, especially on the oxygen. So when you're looking at CO2, it's those electrons that give it the magnetic character. Now we'll use our recycled colored pencil. See how these come in, okay? So you got 2 lone pairs of electrons out here. They create an overall negative, we call it delta negative, which makes the carbon a delta plus. This gives another delta plus. There's electron density we talk about, and it's magnets. So you got a lot of negative, called negative north pole. How about that? That works. N for N. So whenever you see a magnet, think of north pole. For N, think negative. So these are the negative electron parts. That'll work with the N too. Watch this. When you've got N, this is our amino alien, okay? You got your nitrogen. You got your 3 hydrogens. This is an amino. This is the ammonia alien, actually. Save our colors here. We better save our purples. Alien. Okay, now why does that look like an alien? 2 electrons are in that bond. 2 electrons in this bond. 2, 4.